Just to finish the Debye model, the vibrating solid or a solid having a sound wave passing through it, we have the Debye function which will tell us how this heat capacity will go to zero. When you integrate by parts that expression, you get this function. And we can study that function at low temperatures and high temperatures limit. Let's look at the high temperature limit. Temperatures much greater than the Debye temperature. If you expand in this form, you get the Debye function as 1 minus x0 squared, 20 plus, etc., other terms. For large T, that's what you find. And as T goes to infinity, which is the classical limit, CV goes to 3n KB, which is the classical limit, isn't it? So you get the classical limit correctly. In the other limit, as T goes to, or T much smaller than the Debye temperature, for this, which is the interesting limit for us, temperature going to zero, that means x0 is a very large number. You can approximate the function as follows. Debye function. In this limit, you can write the function as plus terms of order e to the minus x0. If x0 is large, e to the minus x0 goes to 0. So you can approximate this as 4x to the 4, 5x0 cubed, or 4 pi to the 4 over 5 t over theta d cube. Here comes the t cube, experimental t cube dependence, which is the correct dependence. As t goes to 0, this function goes to 0 as t to the cube. That is the success of this model. So CV then goes like 12 pi to the 4 over 5 nkb T over Debye temperature to the cube. That's what we were looking for, a successful model that gives you the experimental T cube dependence as temperature goes to 0, CV goes to 0 as T cube. Now let's compare. This is also a preparation for what's coming. CV in units of NKB. Well, the part that we have found was something like this. This is the lattice contribution. Vibrating solid, in other words, gives you a heat capacity of the sort. Now, a solid is not only lattice ions sitting at lattice points and vibrating. It also has electrons, isn't it? Huh? A solid, picture a solid. When you bring together atoms, the first overlap of wave function is the overlap of valence electrons, isn't it? So if an electron is going to go free or will go to a region in between atoms, like in covalent solids, or jumping from one or going from one to the other, creating an ion, like in insulators, there are electrons affected by bringing together the atoms. These are valence electrons. For example, if you try to synthesize a sodium metal, sodium with 11 electrons, 10 electron is just the core electrons with sodium nuclei, and this 10 electrons creates a +1 ion, charge +1. The 11th electron becomes free because it's a metal. So when you look at the contribution coming from electrons, they also have a capacity to absorb heat, isn't it? So they can contribute to the heat capacity. But their contribution is way down, very small. Something like this. We have learned that lattice goes to 0 as T cube. Electrons are linear at lower temperatures. Electrons goes like T. So they dominate at low temperatures, isn't it? When T is small, T cube is even much smaller. So the heat capacity at low temperature end is dominated by the electronic contribution. But at higher temperatures, electrons will not contribute at all. They are very small. Eh? And the reason for this will come clear when we discuss the fermionic problem, the values. Well, why don't you read more about the Debye model? It is a successful model. Huh? What I want you to do, homework, you have to drive the form of the wave, the density of states by using the concept of phonon and its omega versus k dependence. Especially, that's what I want you to be able to do. So, homework, why don't you look at the form of GW, especially by looking at omega as Vs times k. This is velocity of sound times the wave number. Well, that completes the discussion of bosonic systems, ideal Bose gas. Let's summarize what we have done. We have studied the boson gas in general terms as a gas. What we have done is thermodynamics. Then we have specified the models. We have studied the two important problems. Before that, we have discussed the Bose-Einstein condensation problem, how this general thermodynamics shows us that there's a possibility for condensation, all the particles starting to go to the ground state. And then we have done the blackbody radiation, the gas of photons, and today the gas of phonons, the vibrational part of the solid. Now we have to go to the fermionic problem, Fermi systems, if you don't have any questions. Do you have any questions with this? You have to ask me questions. Don't forget this picture. Okay? Electronic contribution, ionic contribution. Because in the fermionic part, we are going to find the electronic contribution. Why is it so small? Okay. Ideal Fermi systems, no interactions yet. Just like bosons, we have to do the general thermodynamic behavior of the gas, starting from general expressions. I'm not going to do lengthy calculations. I will give you the photocopies as I did before. Okay? But let's remember the general expressions we have derived before. For example, we have seen that the quantity PV over kBT, which is also known as ground potential, was found to be logarithm of the ground canonical partition function, which is found to be, again, ln 1 plus z e to the minus beta e. Check these. We have found these relations before. We have studied them. The number of particles, average number of particles, these are all defined to be sum over average occupation numbers. E is the corresponding energy for the state. And that is the usual Fermi-Dirac distribution function. Now we have plus 1 instead of minus 1. Here beta is, as usual, 1 over kBT. Z, the fugacity, e to the beta mu, chemical potential. Beta is 1 over kBT. And if you want to write the explicit temperature dependence, it is mu over kBT. There is a huge difference between Fermi gas and Bose gas. Here, unlike the Bose gas, Z is unrestricted. Here, it can go from 0 to infinity. Do you remember what was that in Bose gas? From 0 to 1, wasn't it? It is unrestricted. Well, summations can be done. How? Summations can be turned into integrals of the same thing, but you have to multiply by the density of states, isn't it? Corresponding density of states. Whatever you are summing, you should use the corresponding density of state, which depends on whether you are dealing with three-dimensional, two-dimensional, or one-dimensional system, or a model. If you do that, PKBT turns out to be G, a number, lambda T cube, F5 halves Z. Remember this, where we have found the expressions in terms of Fermi-Dirac functions. Instead of G functions, here F functions. And our V came out to be G over lambda T cube, F3FZ, with lambda T cube over the volume per particle, GF, 3Fs, Z. We have found these general expressions. Here I introduce a weight factor, if you like, which is G, this thing. It's not a function at all. G is the weight factor. It comes from the internal structure of the particles, like spin. It mainly comes from spin. In our case, the most important quantum number, if you like. So the G is 2s plus 1, which is equal to 2 if we are dealing with electrons as fermions. Electronic spin is 1/2. 2 times 1/2 plus 1 is 2. So in our case, G is just a number 2 for electrons. Here, lambda T is thermal wavelength, extremely important. I am summarizing what we have found before for you. So lambda T, the thermal wavelength, is H over 2 pi mkBT square root. That's mean thermal wavelength. And Fermi-Dirac functions they are given in your book with all their properties in Appendix E. So please take a look. And they're defined as 1 over gamma nu, 0 to infinity, x nu minus 1 dx, z minus 1 e to the x plus 1. Okay. An expansion goes like z squared over 2 nu plus z cubed over 3 nu, etc. So all the properties of these functions are quite well known. Well, I will give you the calculation. These results are going to be found in these calculations. So we save some time instead of doing that. Okay. Let's see. What do we find for thermodynamics? Let me summarize it so that you can find the calculations in my notes. On top of these expressions, we have the following. In one calculation, I show 1 over small v n bar over capital V is 1 over lambda t cubed f 3fz. I have written that probably, so you can find the derivation here. Okay? That's one derivation. Of course, when you look at the internal energy, you have the general relation, 2/3 U over V. I have written this before too. Specific heat comes from derivative of U with respect to temperature using the property 1 over Z del Z del T, keeping volume constant, minus 3 over 2T F3 halves Z F1 half Z. Using this, you can find the expression for heat capacity too. So heat capacity or specific heat in terms of that unit so we can get the general expressions for thermodynamic quantities. Then, of course, we are going to study high temperature and low temperature limits. Helmholtz free energy comes out to be as follows. That is nothing but Gibbs free energy. So it comes out to be NKBT ln of Z minus F 5Z F 3Z. So we have the general expressions for everything we want. Entropy, by definition of Helmholtz free energy, if you like, comes out to be NKB So we have the general expressions for thermodynamic quantities in terms of Fermi-Dirac functions. Well, if you want to determine various properties of the gas, we have to be able to deal with these expressions, right? We have to know these functions, Fermi-Dirac functions. Well, it is customary to go to the limiting forms. What happens at low temperatures? What happens at high temperatures? High temperature is the classical limit, isn't it? So let's work out these expressions a little bit more in these two limits. So your first job is to be able to drive these general expressions in terms of Fermi-Dirac functions, and then see what they are at low temperatures and high temperatures. I will give you the calculations, so you don't have to worry about it. I have the whole series of calculations. I shouldn't repeat that in class. Losing time. Instead, let's concentrate on the physics. Why are we doing this? Well, we want to learn the fermionic character of particles. What do they do? How is the thermodynamics coming out? Now, limit 1 is low density, n is small, n is total number of particles per unit volume, total volume. So this is number of particles per unit volume in terms of this. We are at the low density limit and very high temperatures. We are going towards classical gas, aren't we? Yeah. In this case, we have very small z value. Remember, it is e to the beta mu, mu over kBt, so very small z values. Let's call it small z. In this limit, that's what we can use. If this is the case, then this f(3)z, for example, which is nh cubed divided by g 2 pi mkBt to the power 3s, that must be very small, isn't it? It is proportional to n, which is a small number itself. And high temperatures making it even smaller, dividing with something very large. So, Z, very small. In this limit, we call the gas highly non-degenerate gas. Non-degenerate. Fermi gas. So going towards the classical limit, highly non-degenerate gas. Degenerate gas, Fermi gas, is the opposite limit. Temperature going to 0, Z becoming large. Okay? So, in this limit then, these Fermi-Dirac functions are of the approximate value of Z, proportional to Z. Well, in the expansion, you remember, Z is the lowest expansions. Z square is even lower. If Z is small, Z square is even smaller. 0.5, take square, 0.25, isn't it? Smaller. Always so. So, this is one limit. The second important limit, the low temperature limit. So in that limit is low temperatures and high densities. This is the quantum limit, if you like. So that is large Z limit. Fugacity is large, so that lambda T cube over GV is very large, greater than 1. We can expand the functions, Fermi-Dirac functions, in powers of ln z to the minus 1. And we call this limit degenerate Fermi gas. So that quantity n lambda T cube over G goes to infinity, that means temperature goes to 0. very low temperature limit. Okay, I will give you what happens for this gas at those limits in a moment, but let's take photocopies of these lecture notes. You can do it here. See how I find them. So that I don't have to write that down on board for nothing, just calculations. So you have the calculations, okay? It is better to discuss the physics.